It is my pleasure to introduce our next speaker, Dimitri Rebogin from Kent State University. The title of his talk is on plotting bodies and related topics. Yes, please.
Yes, first of all, I would like to thank the organizers for the opportunity to give a talk here. Today, I'm going basically to speak about the state of art. I'm not going to give any proof, maybe unless you ask some. So, what I'm going to speak about some questions related to floating bodies with the applications, with the applications of harmonic analysis to these problems. And I would like to start with a simple question that is classical. So a classical question, classical. Everybody knows that, but I just want to recall as a playground. This is the question where the harmonic analysis is an indispensable tool. So we are going to speak today about convex bodies. K is going to be a convex body in Rn. Yes, n greater to equal than 2. But please think in the following order. When I say k, please think that n is equal to 3. So usual sense, yes. Then please think about n is equal to 2, and then about your favorite dimension greater to equal than 2. Okay? So I have a convex body in Rn, something like this. And I'm going to be given a family of planes or hyperplanes. I will write H be a given family of hyperplanes. I'm going to define them precisely, but please think that for any hyperplanes, maybe hyperplanes H. And what I'm going to wish is that for any psi, for any direction, this is going to be a unit sphere in Rn. For any direction, we have there exists unique H from H. So I'm going to give a very simple example at the beginning. So if I take a unit direction psi, I am going to put psi perp to be the set of all vectors in Rn that are orthogonal to psi. This is the usual scalar product. In product. So in the picture here, for example, the origin is here. I take my psi, that's the origin, and this is my psi perp. And then I have a section of my body by this hyperplane. So we are going to consider K intersection psi perp. And then the question is as follows. So assume that for any psi in Sn minus 1, the volume, the area, if we in 3 dimensions, the area of the section of K by the hyperplane passing through the origin is constant, where the constant is independent of psi. Okay, assume that this is our condition, and the question is, does it follow that K is the Euclidean ball? Okay, so again, so I have this body of mine. I take this plane, I measure this section, this is the area, and I know that if I take another direction, another section here, and if I take the third direction in this section here, all of them have the same volume, the same area in R3. Does it follow that the Euclidean ball is the only body that satisfies this condition? And this is a classical thing. It is known to be yes, provided, of course, K is equal to minus K, so K is origin symmetric. If K is not origin symmetric, this is false. And here, this is exactly where you need the harmonic analysis. And I'm not familiar with any proof of this result without harmonic analysis. So everything is reduced here to the following statement. If all Fourier coefficients of a, let's say, of a continuous function, if all the Fourier coefficients are zero, then the function is identically zero. This is essentially what it is. Okay, very good. So just one little remark. So a remark. If we change, say in R3, the area by the perimeter, in a moment I'm going to be more specific, then the question is open. So what I mean is that if I have this body K, let's say origin symmetric, and then I have this origin here, and then I have this direction xi, and I have this xi perp, and I have this section now. This is K intersection xi perp, but now I measure the perimeter, the length of the boundary, yes? So if dk is the boundary of K, then what I want, that, let's say in R3, the length of the boundary is constant, where the constant is independent of the direction. Does it follow that K is the Euclidean ball? This is open. So, and again, the reason apparently lies in this harmonic analysis business. This I already don't know, because in the first question, the area of the central section of an origin symmetric convex body is a convolution, but the perimeter is not. Okay, so now let's go to a more general thing. So now we are going to put our bodies in water. So we are going to do the following. So now we still have K convex body in Rn. Now not necessarily origin symmetric. And what we are going to do now, we are going to specify a family of planes parameterized by these directions. And I'm going to specify them in a very special way, but it's not necessarily, you can in principle take anything you like. So if, for example, if you're in R2, like in this picture, you can in principle take any family of lines and ask any question you want. You will see in a moment what I mean. But how I want to do it, I want to fix number delta between 0 and the volume of the body. And please fix it once and forever. It is independent of anything. And then what I want to do, I want to say that I'm going to consider, maybe let me make a picture here. Let me erase this, and I will make a better picture. So I have this body of mine, K, and I am going to have this plane. This is h of psi. Yes, and I'm going to have this section here now. But what I'm going to do, I'm going to define h of psi. This is going to be my plane. This is the set of all x of psi dot psi is equal to t. This is just some real number as some arbitrary plane. And I'm going to put the underwater, think that this is the water surface, okay? So this is the underwater part, I will put h minus of psi, and the above the water part, half space is h plus of psi. So I'm going to define h plus minus of psi. This is x from Rn. So that x dot psi is greater or equal than t or less or equal than t. Okay. So maybe let me put t here. T is an r. Okay, very good. And so my condition will be that we always assume that the volume of the portion of the body underwater is this fixed delta we started with, independent of anything. Okay, very good. So now we are going to ask questions. It turns out that there are two surfaces that are closely related to our case. There are two objects, two important bodies that are closely related, to K. Okay, so the first one I will draw now pictures in R2, but you can draw them in any dimension. So I have this K, I have this H, again H of Xi. We assume that this part has volume delta. Yes, so this is H minus of Xi. So we know again, I will recall H minus of Xi, the volume of this is delta. And now what you want to put here the center of mass of the underwater part. Let me call it 6 psi. So 6 psi is the center of mass of the underwater part of, well, let me write it, of K intersection H minus of psi. Okay, and then what I'm going to do, I'm going to consider the following surface. I'm going to consider, I will define it as delta of K, which is going to be the set of all of the centers of mass in all directions. So in the picture, so if I take another one, I'll take here, and if I take this one, I'll take here the center of mass. If I take this one, I'll take here the center of mass. And in principle, I have some set here. But it turns out there is this theorem of Dupin, or Dupin, maybe. This is always a convex surface. And so the picture indeed is much more beautiful than I drew. It's indeed something like this. Okay. And I'm going to define my first object. The first object is this B delta of K, is the convex body with the surface as delta K. Okay. I just take convex hull here. And this is my first object, B delta of K. And the second object, so this is the union of all centers, the convex hull of the union of all centers of mass of all underwater parts. And another one, I will define it as K delta. This is the so-called the body of flotation. I'm going to define it at the beginning. I'm going to define it just heuristically, and then you can think it any way you want. So you have this body of yours. This is K. Think 2 or 3-dimensional, and then you have all of this waters of yours. And then what you want to do, you want to take the centers of mass of all of these waters. Now, not the underwater part, but the waters, and you want to take them all. And this is your K delta as a set. Okay, so you can also think that K delta is the envelope of the water surfaces. If you want to, I don't want to define the envelope, but heuristically is the following. So you have this curve here, and then at every point you have a tangent. And so this surface is the envelope of its tangent lines. Something like this, but I want to define it in a different way, slightly different way, in the way that was introduced by Elizabeth Werner and Carsten Schut, also by Baranin Larman. So they introduced the following notion, and we are going to use this one, for example. So this is going to be the following. So I have K, I have this hyperplane, and what I'm going to do, I'm going to take this P is this is H minus of Xi again, and I want to have the volume of K intersection H minus of Xi to be delta. Yes. And what I want to say is that I want to look at K delta as the intersection of all half spaces of all H plus of Xi, so that the volume of K intersection H minus of Xi is delta. This is how I want to define it. So something like this. This is K delta. Again, one can show that this is the union of the centers of mass of I take K, I intersection with H of Xi, and I take the center of mass of the section. Now, not of the underwater part, but of the section. And the question I want to address, this is the main question. Do these surfaces, these bodies or surfaces, this is a convex body always as the intersection of convex half spaces. Do these bodies determine K uniquely? This is the question. And the answer in general, for example, I want to be more specific. For example, if we are given K and L, and let's say delta, we are given, let's say, minimum. Well, let's write it like this. Delta is here from 0 to the minimum of volume of K, the volume of L. Yes. And we know that, let's say, K delta is equal to L delta, and B delta of K is equal to B delta of L. Does it follow that K is equal to L? This is a open question for n greater or equal than 3. And this could be done if n is equal to 2. I don't want to enter into this, but if you're interested, I can send you the references. These are 3 theorems of Dupin, of Dupin. And they give the answer that yes, in the two-dimensional case, the answer is affirmative. And there are many instances of this problem, and people usually reformulate this question, but let me just specify 2 more questions that I wanted to address. So question A, sub-question A is what if we are given, what happens if we are given a certain relation, if we are given a certain relation on K, let me change the color, on K, B delta of K, and the K delta. What happens? No, I will give you or maybe some conditions on the surfaces and some particular cases. Question number B. Some particular case is what if, for example, if the simplest case, if K delta is the ball, Euclidean ball, B is always, I mean, the ball, yes. Does it follow that K is the ball? Or similar question, if B delta is the ball of K, does it follow that K is the ball? Those are very interesting questions, and here a notion of material behind this. If I have some time, I'm left only with 8 minutes. So very, very briefly, for question number B, if n is equal to 2, the answer is yes to this question, to the following. Yes, and n greater or equal than 3 open. Here, if n is this blue one, yes, if n is equal to 2, then in general open, but the answer depends on delta. Yes, for some delta, it is affirmative, and for some no. For others, no. Yes, but the full picture again is open. If n is greater or equal than 3, then again, the first question, so k delta, the ball, does it follow that k is the ball? This is open. And again, if you think about it, well, the question I started with, this could be considered as a degenerate case of this one, and for n greater or equal than 3 for the question b delta is equal to the ball, does it follow that k is the ball? Here, Schneider and I'm sorry, let me write Schneider properly. And Falconer, they proved that yes, if delta is equal half of the volume and the body is origin symmetric, and it's known to be that it is null if k is not origin symmetric. I mean, it's not symmetric. Let me put it like this. So for the same density, for this density for half, for other densities it is open. So for the density delta that is not half, it is open. Okay. And so those are the questions where you have a specific condition on one of these auxiliary objects, but you could also have a question on the relationship between them. So let me mention several other questions. So probably the most classical, one of the most classical. One of the most classical is the following. So this is the question again of Elizabeth Werner and Carsten Schut. This is about 90s. Yes, so they ask, what if you have, what if k delta, this the body of flotation, is proportional to k. Lambda is some real number, well, let's say positive number. It's a matter for us. This is the question. And so again, I will make a picture. So this is k. You chopped off this waters, and then you took the envelope. And there is this k delta, and you are lucky that they look the same. The question is, does it follow that k is an ellipsoid? And this is open in general. And I will say a couple of words about this question. I have 4 minutes. Okay, so what is known about it? So again, the general thing is open, but let's say if n is equal to 2, in the two-dimensional case, I mean, I have to mention the results. Let me write the names. I have to mention the results. I don't want to enter into technicalities. There are results of Schut, Werner, and Stanko. I don't want to enter into this, but I will just say the recent developments. Okay, so n is equal to 2. There are 3 guys who gave an absolutely gorgeous proof. Let me find their names because, yeah, here we go. So Ayala, Figueroa, Hieronymo Castro, and Jimenez Lopez. I apologize for my pronunciation of their names. They gave an absolutely gorgeous proof. The proof should go to books that if delta is such that k delta is exactly half of k, and K is origin symmetric, and K is in R2. Again, I emphasize here. Hmm. Then they prove that the answer is affirmative, yes. So K is an ellipsoid. On the other hand, we know that, and this is the only result, by the way, in this full generality that is known so far, and the proof is just I stood on my knees, so beautiful, and highly non-trivial proof. But we also recently, together with Maria Alfonseca, Fyodor Nazarov, Alina Stanko, and Vlad Yaskin, we also show that if, in general, if delta is very close to half, then the answer is negative. So there are bodies, there are bodies on the plane, that satisfy the condition. Well, maybe not necessarily with this, not necessarily maybe with this coefficient. They satisfy this condition for some lambda. Yes, but they are not ellipses. And this is again only on the plane. There are, I have 1 more minute, I will mention. So there are also results for, you could also ask a similar question for the surface of centers. Yes, and you could also ask, for example, because there are three bodies, you could also ask the question about the relationship between these two. And does it follow that K is an ellipsoid, and does it follow that K is an ellipsoid? So I have to mention that this was done recently on the plane for K close to the Euclidean ball. It was done by my student Vincent Shaw on the plane. And this thing, an absolutely astonishing proof by Bartek Zawalski. He proved it recently only for very specific, I don't want to enter very specific delta. Specific delta, but fixed. Yes, so we fix delta, and he did this, that the answer is yes in both cases. So maybe let me stop here. I just began, but anyway, just warmed up. Thank you very much.